Hi guys, it's ready for the sound video. Say hi guys.
Hi.
That's Bethany. Bethany, get closer. That's Bethany. That one's Owen. Okay.
Hi.
No more talking.
Bye-bye.
No more talking. Okay, so let's get started. Computer's a little slow today. A lot slow today. It's not moving. There we go. Okay, I want to refresh your memory what you did yesterday, or maybe you did it today, but you did this lab. So watch this video. It has awesome music. Okay, so that's a tuning fork, remember? You put the tuning fork in the water, and you notice some splashing, right? It wasn't as dramatic as this. So there's a tuning fork in slow-mo. Notice the vibrations. Depending on your tuning fork, you may not have seen vibrations like that. So, your tuning fork... I'm going to pause this video. It's driving me nuts. I'll let it go one more time. So, your tuning fork's prongs vibrated at a certain frequency, and that number was stamped on the side. Those vibrations might have been too quick for you to see, but when you put them in the water moved because that mechanical energy was transferred from the tuning fork to the water. So the whole point of that lab was so you can see that the sound is energy, and the energy can be used to do things, like move water. Sit on your bottom. Oh my gosh. It's a bad idea.
The students sit on your bottom.
Okay, so it says make your foldable. You need to grab this from the bin. It looks like this. And you're going to fold. It should be a full piece of paper. Alright, let me focus on that. There's 2 dotted lines. Fold on those dotted lines. So now you'll see it says glue this side down and then here. And then you'll make 2 cuts. You're going to make a cut across the line here and a cut across the line here. Now you have 4 tabs. Challenge and regular, you both have this foldable. Okay, so what is sound? Open up the tab that says what is sound on top. Open that up. You're going to write this inside. So the definition of sound, the official scientific definition, is sound is a disturbance that travels through a medium as a longitudinal wave. So we talked about longitudinal waves before, and that's a wave that vibrates the medium back and forth. So the sound all starts with a vibration. You can see the longitudinal wave. You got your rarefaction here. You got your compression right here. Another rarefaction. Another compression. And then another rarefaction. So those, all the red dots represents air molecules that are vibrating in place. And it's like dominoes. These molecules start vibrating, which knocks into those, which knocks into those, which knocks into those, all the way to the ear. So think about it. If I'm talking to you in class, I'm vibrating the air inside my mouth, which vibrates the air outside my mouth, all the way to the ear next to your ear. The air in my mouth does not go to your ear. That's kind of gross. It vibrates all the way to the neighbors till it hits you. How sound travels. So now you're in the bottom tab where it says how sound travels. Open that up, right inside. It travels all around the source. Sound is different than light. You have to be in front of the light to see. Sound goes all around the source. It requires a medium, therefore sound does not travel in outer space. The most common medium, you might not be able to see it here, air. We use air all the time to talk to our neighbors. I do want you to include this picture here. So the alarm clock is buzzing, and then the air all around it is vibrating. So if I'm standing over here, that's a great picture of me. Put my dress on me, some legs, an arm or two. If I'm standing over here, I'm going to hear the alarm clock. If I'm standing over here, my pretty dress, some arms, I hear the alarm clock. No matter where I am in the room, I'm going to hear the alarm clock because the sound travels all around the source. The reason there's not dots below is because it's sitting on the ground.
Buzz.
So draw that into your notebook.
Buzz, buzz.
Okay, parts of a sound wave. Owen? So it says parts of a sound wave. Open that tab up. It's going in the top area. Sound is longitudinal. So make sure, I don't know why I use such a light color. Maybe we go over that. Sound is a longitudinal wave. And I want you to draw this picture. You got your tuning fork, and I want you to draw the compressions and the rarefactions. Okay? Take a minute. You might need to pause the video to get that sucker drawn. Okay, finally, this is an advanced concept. So let's write advanced down there. Ooh, advanced. So this is a tricky concept. This is called the Doppler effect. The Doppler effect occurs because there's motion of the sound source, which causes the waves to either get closer together or spread out. So this example, I hear the Doppler effect all the time with NASCAR, as if I watched the races, but I could. Ambulances as they pass me by, or police cars as they pass me by. So in NASCAR, if you're watching a race, bless your soul, because they're kind of boring, but the cars go vroom, vroom, vroom. Ooh. Kind of tickles when you do that. Yep. If the car is sitting still, the car just goes. It makes a consistent noise. Owen, do you need to leave? Okay, if the car is at the starting line, it makes a consistent sound. But as soon as the car is going a couple hundred miles an hour, you'll hear that constant noise, that changing in pitch. That's because of this picture here. Let me switch the screen. Oh, Bethany? No. Okay, so you got the car moving, and that is squishing these sound waves up here. The closer the sound waves are, the higher pitch they are. So these are high pitch. If the sound waves are far apart, like behind here, they get a low pitch sound. So the closer the sound is, you get a high pitch. And then the reason these are close is because the car is moving in this direction. And the car is actually squishing its own sound waves. And so it sounds very high pitch here. Over here, it's moving away from these sound waves, so it sounds pretty low pitch back there. So this caused that Doppler effect. As soon as he passes this kid here, that kid's going to hear that vroom sound of the Doppler effect. Vroom. So this person here is hearing the low pitch. This person here is hearing high pitch for now until that car passes. You might be familiar, and I don't have a picture on my screen of this, you might be familiar with planes and stuff breaking the sound barrier. So if these sound waves if the vehicle is going so fast, he passes his own sound waves, that makes a sonic boom and a sonic blast. You might want to consider, after the video is over, just Googling sonic boom, and you'll see airplanes that break the speed barrier all the time of sound, because sound only travels 500 something miles an hour. Okay? That's about it. If you have any questions, please come see me or Miss Burkhart. Guys, do you have anything to say?
Bye. Hope you have fun learning. And I hope you have fun eating all the candy.
Oh, yeah. They're giving you all their Halloween candy. You're welcome.
Yeah, why in sheep?